Okay, this is Dr. Morton. This is the video for Friday, for Monday, the 26th of February. And so I'll be back on Wednesday and see you then. In this video, I want to cover Chapter 7, and I'm not going to spend a long time on it because the material is not that much, but I do want to go through this so you have a good sense. So first, let me transition to the book, and then I'm going to go to the slides. So, all right, so here we are. And what you see here, we have the basis of combinational design. All right, so these are the learning objectives. I want you to be able to list and perform the basic steps in a simple combinational design. I want you to be able to describe and work through two methods of simplification of a combinational design. And I want you to be able to explain why don't cares can arise in a combinational design, how they can help with simplification. And finally, describe how to realize the design and hardware in both and networks. In other words, SOP and POS. Okay, so there are several things we want to cover here. First off, there is a little video you can watch here in addition to the one I'm going to do. And that should just give you a little more material to work with. Secondly, here are the steps. So let's just go through these. So first of all, you want to define the inputs, which are the independent variables. And if you have n inputs, then you're going to have 2 to the n rows in your truth table. You also want to define all the output functions. And those are the dependent variables. And we'll say you have m outputs. So n inputs, 2 to the n rows in the truth table. And then you have n plus m columns. So if you have n independent variables, say A, B, C, so that would be 2 to the third, or 8 rows in your truth table. Let's say you have 2 output functions, F1 and F2. So then you would have your 3 columns for your independent variables, that would be n, plus 2 columns for your functions, m equals 2. So in this case, n plus m is 5. So you'd have 5 columns total and 8 rows. Every time you add an independent variable, you're going to double the number of rows. Every time you add another output function, all you're going to do is add an additional column. All right, so that's important. So the first thing you do is you identify your independent variables, you identify your outputs, or your dependent variables, and then you construct your truth table. And again, it's going to have 2 to the n rows. It's going to have n plus m columns. And then once you construct a truth table, you need to determine the desired value for all of the output functions for each row or for each combination of input variables that actually can occur. For the ones that will not occur, if there are any that won't occur, you can pick your output value to be whatever you want. And that's what we call a don't care. And again, it's not that you don't care about the output value, it's that it won't ever occur, so you can choose it however you wish. All right, and then basically we want to figure out what kind of form of our solution. Are we trying to build an integrated circuit? Are we trying to use discrete components and make a circuit? Are we trying to program it with a microprocessor? Are we trying to set it up as programmable hardware like with an FPGA or a CPLD? And we'll talk about those devices later, not today. And then we want to minimize the logic expression. So normally the way we do that, if we don't have too many variables, we'll use a K-map. And if we have too many variables, say more than 5, then what we'll do is use a computer-based tool or switching algebra. And so once we get it minimized, we're going to minimize it in the form we need. And that depends on our target hardware. So usually when we create a solution, we don't use AND and OR gates to implement it. Now you can, but normally for convenience sake, we map it into a single gate type solution. And there are 2 gate types that make this real doable. One of them, NOR gates, and we can have a NOR-NOR network. if we do the NOR network, we have to start with a POS design using the max terms. If, on the other hand, we're going to wind up with AND network, so where we just have AND gates, we'll start with an SOP form. And so normally we do our design work in SOP form, and then when we've finished the design work, then we convert it to a NAND form. Or, again, obviously, if we're doing POS, if we're doing NOR, we'd use POS instead. All right. And then finally, we'd entered into our either our integrated development environment to make chips, or an integrated development environment to program hardware, or maybe we'd then translate our equations into, perhaps we'd implement it with a computer program. And then finally, we'd often simulate it in our integrated development environment so we know it's going to work properly, including we'd even put in potentially some delays, some information about time delays so we could get our timing closure. All right, and then we would either generate the bit file to program a programmable device, or we'd generate the set of photolithography steps that we need to take in the foundry to make the integrated circuit. All right, so again, we're working with this model here where it's inputs, a network, and some number of outputs, at least one, maybe more. And so here's an example. Here's our truth table, and we see that we have ones desired for min term 7, 6, and 5, or 5, 6, and 7. And the max terms 0, 1, 2, 3, 4. So we can solve it by doing the three min terms, which would be f equals ab prime plus abc prime plus abc, or we could do it with the max terms. And generally, we're going to put it into a truth table. So in the truth table, you could see the min terms would take these two functions. The max terms would take this four variable these four boxes grouped together here, and these two boxes here. So that would be so that would basically be A plus this group of two, which would be B plus C. So A times the quantity B plus C. Or, in this case, we would have AC plus AB in the POS form. So let me write that so you would have, so you know what that is. So we do this. So we would, so here's our K-map. We have these three ones here with two groups of two, and then our max term, our POS solution, then would be this group of zeros and this group. So this one just resolves to A, and this one resolves to B plus C quantity. So our max solution, F, equals A times B plus C, and our min-term solution is A B plus AC. And of course we can factor the A out, so that would be A times B plus C, and now you can see we're back to the SOP solution. All right, so that's a good example of how we do this. The customer gives us the truth table. The truth table turns into a K-map. The K-map turns into a SOP and a POS solution, and we pick the best. In this case, the POS solution is slightly simpler. It only has two gates, and 1, 2, 3, 4 inputs, whereas this has the SOP solution has 1, 2, 3 gates, has an AND gate here, an AND gate there, and an OR gate there. And here we just have one OR gate here and an AND gate, and this goes directly in, that goes in. So here you have 3 gates and 1, 2, 3, 4, 5, 6 inputs. Here you have 2 gates and 4 inputs. So clearly the POS is simpler. All right. So moving on. So that's what the hardware would look like when it's all said and done. Notice that the POS solution with an input OR gate and an output AND gate, and here the SOP with 2 input AND gates and 1 output OR gate. This POS solution is clearly simpler. But if your target was NAND, you'd have to use this anyway. All right. So we did talk about functionally complete 2-layer networks, and if you'll remember, we've done several of those. First off, we have AND, OR, and you also have to have inverters, or and also inverters. Then you can have NAND, and that comes from our SOP form. So this is SOP, and then we have NOR, and that comes from our POS. All right, so those are the 4 commonly used ones. Now there are 4 others, but we're not going to really. I'll mention them briefly in passing at one point. I think I already have. I will again later. But for now, this is really these are the functionally complete sets of gates that we're interested in. Okay, so let's see. Yeah. All right. So you remember the alternate symbols. Well, here all the functional complete sets. So the ones with the so the ones with the stars are functionally complete. So for instance, OR AND, that's fine. OR NAND, that's fine. NAND AND, that's okay. NAND, that's also functionally complete. AND NOR, AND OR, NOR, and NOR OR. Those are the 1, 2, 3, 4, 5, 6, 7, 8 functionally complete sets of gates. The others are not functionally complete, and you know that because if you use switching algebra, you can simplify them to just an AND gate or just an OR gate, and you know then that they can't be functionally complete because an AND gate by itself is not functionally complete. Okay, and this is how we look at them if we were to work through all of them. You'd start with SOP, and you can then do a double inversion and partial expansion, and you get to NAND. Let me show you what that looks like. It's pretty straightforward. So let's do this. So swap this out here. All right. So let's say we have an OR AND. So we'll just write an SOP form. Let's say F equals A prime B plus AC plus CD. Okay, so that's our going in equation, and we want to convert this to NAND. How do we do that? Well, all we have to do is put parentheses around it and invert, another set of parentheses and invert. So that's a double inversion, and if you completely expanded it all out, you'd get back to just your inner expression, because with 2 inversions you haven't changed anything. But if you just partially expand, here's what you get. We'll just take this one invert and we'll put it inside, and we'll have A prime B inverted times, because we have to invert the sign, the quantity AC inverted times CD. And then all this still has one inversion left. So notice this A prime B with in parentheses with an invert, that is a NAND gate. All right. In fact, let's look at all the different possible ways we can do the gates. An AND gate looks like AB. We'll just put that in parentheses. An OR gate is A plus B. A NAND gate is AB with an invert on the parentheses. And a NOR gate is just A plus B with an invert on the parentheses. So this is how we recognize ANDs, ORs, NANDs, and NORs. All right? So if you look at our equation here, this is a NAND, this is a NAND, and this is a NAND. And notice, if we substitute, say if we call this X, and this Y, and this Z, then we can substitute in, and we have X, Y, Z, all inverted. That is another NAND gate. So this is a NAND network. In fact, it would look like this. There's your NAND gates. This is A prime B. This is AC, and this is CD. And they would all have an output bubble indicating that they're NAND, and they would all go into another NAND gate. And this is your output F. So it's a NAND network. And whenever we want to convert to NAND, we have to start with SOP. If, on the other hand, we want to go to POS, then we have to start. Go to NOR, then we have to start in POS form. So let's look at that. So in POS form, we would start with, say, A plus D prime quantity times B plus C times A prime plus C. All right, something like that. All right, we want to switch this. Same thing. We do a double inversion. We partially imply this into the inside. And when we do that, we're going to put tick marks on all these. And then we're going to change these AND gates, this AND gate, to a NOR gate actually. And so if you look at this, quantity A plus D prime inverted, that's a NOR gate. Quantity B plus C inverted, that's a NOR gate. Quantity A prime plus C inverted, that is a NOR gate. And then the whole thing, if we substitute in X, Y, and Z with our, and we have this external parentheses, and again, we got rid of this one because we put it inside. Now we have a tick here, that's a NOR gate. So this basically then becomes a NOR gate here, a NOR gate here, a NOR gate here, and one output NOR gate. So this was A and D prime, this is B and C, this is A prime C, and they all feed in here, and that's F coming out. Now notice this implementation is totally different than the one we just looked at. They wouldn't necessarily be equal because they're totally different. But this, if you start in POS form, then you get to NOR. And if you start in SOP form, like here, then you get to NAND. Now, part of the reason I'm having you do this, the final project, is because that's going to reinforce learning this information. Okay. Now, there are other ones. If you keep going, you get to OR NAND, starting with SOP, you go NAND. If you expand it a little more, you get to OR NAND. You expand it a little more, you get to NOR OR. And if you keep going, you get back to where you started, because, again, a double inversion actually doesn't change the value. So if you fully invert everything twice, you'll be back to the AND OR form. But it's when you partially expand it that you get these different forms. Same with POS. You start in POS, OR AND, NOR NOR, and then there's an AND NOR and a NAND AND, and then back to POS. So the only ones we're really interested in are the first two, SOP and NAN, POS and NOR. But the other ones are also valid. It's just that it doesn't really help us because we like to have just one type of gate when we make integrated circuits, or if we already have a pre-existing hardware, then we already have what's on there, and that's what we're going to use. All right. So remember the alternative symbols. You can also apply these, and we did this before, but you don't have to do switching algebra. You can use these alternative symbols and make this work. So how do you do that? Well, okay, let's say we have the SOP form, A prime B, AC, and CD. So that would be an AND gate with A prime B, an AND gate with AC, and an AND gate with CD. And they would all go into an output OR gate. But instead of the output OR gate, I'm going to draw the equivalent symbol. And, oh, sorry, you couldn't see that. So the equivalent symbol here for a output OR gate, for a output OR gate is an AND gate with inverters on the inputs and the output. So let me do that. Okay, so I'll show you the paper. All right, so here's my gate. This is my SOP form, and normally I'd have an OR gate here, but I'm going to substitute a NAND gate, and it's going to have bubbles on all the inputs and a bubble on the output. Now, because these bubbles, you can always add two bubbles because the bubbles cancel. You can take off two bubbles. You can put two bubbles together if you have to, and you can cancel. You can slide bubbles on wires. So I'm going to slide the bubble here up to here, and I'm going to take it away from here. Same with this one. And same with this one. So now there are no bubbles down here. These wires connect directly. And what we have is NAND gate, NAND gate, NAND gate, NAND gate, NAND gate. So this is now in NAND form, just like this. The circuits are identical. So here I use switching algebra. Here I use the alternative symbols and did it graphically. And you do the same thing with the POS form. Okay. So sometimes I'm not going to spend a lot of time on this because it's actually hard to show it. But if we take an equation like this, A, B, C prime D, A, B prime, C, D, and A, B, C, D prime, we can factor the A out. And now we save one input for every one of these, and so we have 3 input gates, 1 output gate, but our input gates only have 3 inputs. So this is one example. It's not a great example, and there clearly are better examples where our savings could be much more dramatic. But in any event, often we might factor into 3 layers. So at this point, we actually have 3 layers. We have this we have these AND gates, but they go into an OR gate, and then these 3 outputs go into an AND gate, and then the A and these, let me draw it. So let's do that so you can see what's going on here. And okay, so that's probably not the best example, but let's do this. Okay, so if we have say let's do AB plus AC plus AD. Okay, so ADE maybe, something like that. Maybe AC, AC prime B, maybe, I don't know, B prime, something like that. Okay, we can factor the A out, and now we have B plus C prime B prime plus DE. Okay, so if you look at it, so we have a AND gate here, we have an AND gate here, and we have a B by itself, and these all go into then an OR gate, and that OR gate then goes into an AND gate along with this single variable A, and that's our output F. So we have one layer, these 2 input AND gates. We have a second layer, this OR gate, and a third layer, this output AND gate. So when C prime, B prime, D, or E change, we have to go through 1, 2, 3 gates before we get our output. So that adds a gate delay. But you can see here we have 1, 2, 3, 4 gates total. Here we have, well, 4 gates total as well. But here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 inputs. So we have 4 gates and 11 inputs. Whereas with this one, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 4 gates and 9 inputs. 1, 2, 3, 4, and 9 inputs. So it saves some hardware. But there are examples with more dramatic solutions. I just didn't pick a good one here. Okay. All right. So you can also take an expression and generate the truth table, and you can take a given expression and plot it. So if you were given AB prime plus BD prime plus BC, you can plot it like this, and then you can go back and you can read, so you know that works out to be minterm 4, 6, 7, 8, 9, 10, 8, 9, 10, 11, 12, and 13. 12, 14, 15. So that's another thing you can do. All right, and then again, our when we have an incompletely specified function, then we have these don't care terms that we can choose to take as a 0 or 1, depending on what makes our resultant things simpler. So that pretty well covers chapter 7, and I did want to get that in. All right, I'm going to stop this, and then I will also have a recording that's basically just going to talk about how you do. It's going to be basically chapter 8. We're going to talk about 4 combinational devices that are very important. We're going to talk about multiplexers. We're going to talk about decoders, read-only memories, and adders. And we won't spend a lot of time on the adders, but I do want to point out some things about the adders. So that's coming up. All right.